All right, so our goal this morning is to continue talking about circuits. And so far, we've learned how to deal with circuits that involve resistors. We've learned how to deal with circuits that are exceptionally complex yesterday, where maybe you had multiple batteries or just a really, really complex array of resistors. And of course, in chapter 19, we learned how to deal with capacitors. What we haven't done is learned how to deal with resistors and capacitors at the same time. So that's our goal for today, is to do what we call RC circuits, circuits that have resistors and capacitors together in the same circuit. And it's going to pose some special challenges, as will become apparent here in a moment. So let me get my screen share up. Link. So let's build the simplest circuit that I can think of that uses both resistors and capacitors. Here's a little DC battery. And then I'm going to have a resistor of some kind. And I'm going to put that resistor in series with some kind of capacitor. So this is an example of what we call an RC circuit. Now, in order for us to make sense of this RC circuit, we can rely on the fact that the loop rule and the junction rule that we talked about yesterday are going to apply to every circuit ever, right? It doesn't matter what kind of circuit you've got, the loop rule and the junction rule will always work. So let's think through the implications of what those two rules tell me about this configuration. Well, the first thing here is the junction rule. There are no junctions in the circuit that I just built here, which means there's no place for current to split and have some of the current go one way and the rest of the current go the other way. What that tells me is that at any given moment, I'm going to have one current everywhere in the circuit, right? That's cool. So the junction rule tells me I'm going to have a single value for the current. The loop rule tells me that all the voltages around this loop that I've drawn are going to have to end up equaling zero. And that allows me to write an equation. So imagine I start right here and I go around the loop. Now, as I go across this battery, what's going to happen is there'll be a voltage change. And that voltage change is going to be however large the voltage is of the battery itself. I'm going to call that voltage of the battery V total today. Now, when I go across that, let's the voltage increase because I'm going from the negative terminal to the positive terminal. So I've got V total. But now, now I'm going to go around. I'm going to cross this resistor. And when you cross a resistor, there's a voltage change. How much voltage change? You get according to Ohm's law, where it says that V equals I times R. So I'm going to have a voltage change of I times R, and it's a voltage drop, so it's negative. That makes sense. Now, I'm going to then head over, I'm going to cross this capacitor. And when I cross that capacitor, there's going to be another voltage change. And in order to find the voltage change of a capacitor, I'll remember the definition of capacitance is C equals Q over delta V. And that means if I just rearrange that to solve for delta V is going to equal Q divided by C. So, if this is the voltage drop across capacitor, it's a drop, so it's negative. And of course, now I'm back to where I started. So all of those voltage changes will always equal zero according to the loop rule. So right then and there, I have an equation that's going to govern the behavior of this RC circuit. But here's what's interesting about it. All right. Let's say the exact instant that the exact instant that I hook this up, what's going to happen is there was originally zero charge on that capacitor, right? That capacitor started out empty. But as current flows, I'm going to be depositing more and more and more charge on that capacitor. So it may start out empty, but it's not going to stay that way. And that's interesting because Q, the amount of charge on the capacitor, is one of the variables in the equation. So what that tells me is that Q is a function of time. Q is going to be changing as time progresses, and I'll have different values at different moments. But that means that this equation is sort of interesting because as Q changes, the equation has to stay true. So if Q over C is becoming larger and larger and larger with time, in order for this equation to stay true, something else is going to have to get smaller and smaller and smaller in time to trade off for it. And so the dynamics of this end up being a little bit challenging. So in order to think this through, let's imagine what happens the very moment that I first hook this battery up, right? This guy started out empty, and at that one instant in time, for that one split second, the Q on the capacitor equals zero. And if Q equals zero, this whole term I can ignore. And oh, look, I have V total minus IR equals zero. If I solve for the current at that moment in time, I just, ooh, crud, I smudged it. Great. If I solve for the current at that time, I'd add that over, divide that through. I'd end up with V total divided by R is equal to the current. That's the current that I'm going to have at the split second when the charge is equal to zero. But later on, as the charge becomes larger and larger and larger, the current's going to get smaller and smaller and smaller. And so what that tells me is that this is the biggest the current is ever going to get. It starts out that big, but it's going to get smaller as time progresses. So I'm going to call this particular value of current, I'm going to call that I max, right? That's the maximum current that I'm ever going to see. Now, as time progresses and the charge on the capacitor gets larger and larger and larger, the current is going to get smaller and smaller and smaller. At some point, the current is going to get so small that it reaches zero. But remember, the current is how I'm adding more charge to the capacitor. When the current gets to be zero, that means that I've stopped putting more charge on the capacitor. And however much charge is on that capacitor, that's what I'm stuck with. I'm not going to get any extra. That's the biggest the charge will ever get. So if I take this equation and I think about it at a later point in time, when this has reached zero, I'm trying not to smudge it this time. Now I'm going to have V minus Q over C equals zero. If I solve that, for Q, I'd add that to the other side, I'd multiply by C, so I'd have C times V total equals Q. Well, this amount of charge would be the biggest the charge could ever get because the current is zero at that moment. I'm not putting more charge on anymore. So that will be my Q max. So I'll have this current when the charge is zero. I'll have this charge when the current is zero. So I kind of understand like the two endpoints that I'll see. I know what it's like the first moment I hook it up, and I know what it's like when I wait some time later, and I'm not sure how much time that's going to take. But what I don't know is what does the current look like or the charge look like in between? If I hook it up and wait for 2 seconds, I'll have less current than this, but I'll also have less charge than this. So how much will I have? We don't know yet. And in order for us to answer that question and to think about, well, what's it going to look like at those in between times? Well, we're going to have to deal with the fact that everything is changing continuously, which means it's a calculus problem, right? We're not going to do calculus. So what's going to happen is I'm going to have to sort of hand wave and get you this next set of equations. So if I'm thinking about like what this charge looks like as a function of time, I can kind of think about it conceptually this way, right? So if this is how much charge is on the capacitor, at time zero, I got to have nothing. I'm starting out empty, right? And then at some later time, I'm going to have Q max. So I'm going to get up to this level somewhere over here, and I'm not sure where. Now, here's something that I do know. I know the definition of current. The definition of current is the rate of change of charge, delta Q over delta T. And what I realize is that that has a specific interpretation on this graph, because delta Q, that's the rise of this graph. Delta T, that's the run of this graph. The current is apparently the same as the slope of the graph, rise over run. So knowing that, I can kind of deduce what this looks like. Because at first, when we first start off, my current is as big as it's ever going to get. That means my slope has to be as steep as I can make it. So my slope is going to start off very, very steep. But immediately, there's going to be current that's going to start showing up on my capacitor. And as that happens, the current's going to get smaller over time, which means even though it's going to start out super steep, it's going to get immediately less and less and less steep. So it's going to be a very steep line that's concave down. It's going to be curving downward. And what's going to happen is it's curving downward. And by the time I get to Q max, the current will be zero. I'll be approaching a zero slope. So it's going to eventually curve until it flattens out. It's going to flatten out at Q max. So just understanding these two endpoints and how the current is related to Q, I kind of have a sense of what the shape of my graph ought to look like. And that gives me kind of a heads up on what the equation ought to look like. I need an equation that's going to look like this. And here's the equation we're going to end up getting. And to prove this, I'd have to do some calculus, which we're not going to do. So take my word for it. So the charge at any given moment, Q, is going to equal whatever Q max is times 1 minus, and then here I'm going to put in a decaying exponential, negative T over tau. So to see that this equation is going to give me this sort of relationship, think about what's going to happen at time zero, right? So if time zero, then I have negative 0 over tau, that's 0 up here. E to the 0 power, now E is the natural exponential function. It's the 2.718, whatever. You guys probably saw it in pre-cal. It's used a lot in exponential growth or exponential decay, or you'll use it to calculate continuously compounding compound interest. That's a problem you see a lot in your math classes. It's a number. There's a button on your calculator for it. But it doesn't matter what that number is, because anything to the 0 power equals 1. So at time 0, E to the 0 is 1. I have in parentheses here 1 minus 1, which is obviously 0. 0 times Q max is 0. So when I put in T equals 0, I get 0, just like it says. Yay! Now, as t gets larger and larger and larger, this exponential function is going to get smaller and smaller and smaller and smaller. So I'll have 1 minus a number, but as time goes on, I'm subtracting less and less and less and less from 1. And I'll be taking that fraction that's less than 1 times q max, and I'll get some fraction of q max. To see that in a bit more detail, let's work through some values. But in order for me to do some more, I'm going to have to tell you what tau is. Now, it turns out that tau is going to end up being the product of the resistance of the resistor times the capacitance of the capacitor. So tau is equal to RC. We call this the time constant of your circuit. So to see what this time constant does and how it affects it, let's do some little experimentations. All right, so remember, I've got Q equals Q max 1 minus e to the negative t over tau. All right, and let's think about what kind of charge we're going to have at different moments in time. So obviously, if I'm looking at times and charges, if I put in t equals 0, we already figured out that that's going to be 0, right? But this time constant is an amount of time. In fact, if you think about it, if I'm looking at R times C, let's think about the units for a second. R is measured in ohms. That's ohms times farads. Except, what the heck is an ohm? An ohm is a volt per amp. And a farad is a coulomb per volt. So if I'm multiplying volts per amps times coulombs per volts, oh, look, the volts would have canceled. And I've got coulombs per amp. Except, what the heck is an amp? An amp is a coulomb per second. So I've got coulombs per amp. That's the same thing as coulombs over coulombs per second. When you divide by a fraction, it's the same as multiplying by the reciprocal. So that's coulombs times seconds over coulombs. And oh, look, that's a time. It's got units of time. So let's imagine that I've got a circuit where an RC is like 10 seconds. So I'm going to wait 10 seconds or 1 time constant. How much charge am I going to have at that moment? Well, if tau is the same thing as t, I have tau over tau, that's 1. So I'd have e to the negative 1 power. So I'm going to bust out my calculator and figure out what e to the minus 1 power is. If I can find the button for it, there we go. So e to the minus 1 power is about 0.367. So this thing in parentheses is going to be 1 minus 0.367. That means this fraction is going to be 0.632 times Q max. So what that means is that if I wait 1 time constant, that'll be 0.632 times whatever Q max is. Notice it doesn't matter how big Q max is. And one way to interpret that 0.632 is it's a fraction, it's a decimal, it's a percentage, right? After 1 time constant, I'm going to be 63.2% of the way to full charge. Pretty neat. So you might think, if I'm going from 0 up to Q max, and during the first 10 seconds, I get more than halfway there, I'm 63% of the way to my maximum, you might think that after 2 time constants, you'd be done, right? But you'd be wrong. If I wait 2 time constants, so if this was 10, 20 seconds, well, now I'd have e to the negative 2 tau over tau. The taus would cancel, I'd have e to the negative 2 power. So what is e to the negative 2 power? it's about 0.135. When I subtract that from 1, I get about 0.864 or 0.865, we'll call it. So after 2 time constants, this entire thing has reduced to 0.865. And of course, it's times Q max. So even though I charged up 63% of the way during the first time constant, or the first 10 seconds, the next 10 seconds, I only went from 63.2% up to 86.5%. So my little progress bar has not jumped up nearly as much during the second period of time as it did during the first period of time. Why is that? Well, remember what's happening is my curve is flattening out. So during the first time constant, I went up by a large amount. But during the next time constant, I only went from here up to here. I went up a smaller amount. And so every time I wait another time constant, I'm not going up nearly as far. It's leveling off more and more and more and more. After 3 time constants, I'd have e to the negative 3 power from this, right? So e to the negative 3 is only 0.049. So 1 minus that is only about 0.95. So after 3 time constants, I'm only about 95% of the way to full. And what's happening is as time gets bigger and bigger and bigger, this is getting smaller and smaller and smaller, but it's flattening out. It's approaching 0 asymptotically. And so after 4 time constants, we're up to about 98%. And after 5 time constants, I think we're at like 99.5%. But you can keep going longer and longer and longer. And what you'll find is that you're never going to get to 100%, right? You can wait infinity seconds and never quite reach 100%. However, after 5 time constants, dude, this is so close to 100%, it might as well be 100%. At some point, you're going to be at like 99.999999%. And at some point, you just kind of round off and say, you know what, we're done. And so, the amount of time it will take to get up to 100% charge is infinity seconds, right? But for all practical purposes, if we wait more than about 4 or 5 time constants, it's going to be super, super close. And so in physics problems, you'll often see things where they'll give you a circuit and they'll say, this capacitor has been hooked up to the battery for a long time, right? And when you see a physics problem say that something is a long time, effectively, you should interpret that as being infinitely long, right? That's what you should assume, is that a long time equals infinity. In practical terms, how long is infinity? Well, it depends on what your time constant is, right? If your time constant is 10 seconds, then a long time is probably longer than about 40 or 50 seconds. But if your time constant tau was like an hour, then a long time would be more than about 4 or 5 hours. So it's going to be in terms of whatever that time constant is as to how long you have to wait before you can say, oh, I'm basically fully charged. So that kind of gives us a sense of how the charge increases over time. Now, we said a minute ago that as the charge got bigger, the current's going to have to get smaller. We've got an equation for the charge. What we don't have is one for what the current should look like. However, remember that the current is the rate of change of Q. So I'll use the same sort of logic here that we did a minute ago. We know that as Q gets larger and larger and larger, the rate of change is getting smaller and smaller and smaller and smaller. So the slope of this graph ought to give me what the current looks like at any given moment. So it's going to start out super steep. Therefore, the current's going to start out super big. But immediately the current's going to get smaller and smaller and smaller, and it's going to approach zero. So it's going to be curvy, but it's going to be curvy the other direction. So if I'm drawing out my current graph, I'm going to start off at whatever I max is, and I've got to level off towards zero. It's going to end up looking like that. And of course, I know how to draw an equation that will look like that. It's going to equal I max, and I'm going to have the same sort of exponential decay, but I'm not going to have this 1 minus factor. This 1 minus factor is what makes the charge equation start off at zero and get bigger and level off at a constant rate. Here, it's just going to get smaller and smaller over time. At time zero, this equals 1, puts me here. At any time larger than zero, this e to the whatever factor becomes smaller and smaller. It starts here, it gets smaller and smaller and smaller. So it's tracking down in the exact opposite way that this did. So how long will it take to get to zero? Infinity seconds. You know, after one time constant, I'll go down by, well, this was 1 minus e to the whatever, so it's the 0.37. So I'll be about 30% charged after one time constant, about 15% charged after 2 time constant, about 4% charged after 3 time constants, and so on and so forth. So my current will diminish over time to the tune of that. Super easy. So, of course, we're going to make it more complicated. And to see how, let me draw this doozy of a circuit. Let me see if I can get this done right. So, what I'm going to do is I'm going to have a battery over here. And I'm going to have a capacitor here, a resistor here. But in my circuit, I'm going to have a switch. And what's going to happen is this switch can go 2 different locations. Right? So sometimes the switch is going to be connected from here to here. Other times the switch is going to be connected from here to here. And it's going to go from position A to position B. I don't know why I did it so small. I'm stupid. So it's going to swap. Now, what's going to happen is when the switch is connected here, this right over here is open. So this whole section of the circuit is an open circuit and basically doesn't matter. So when I'm in position A, imagine that's not there, and there's my circuit. Well, that just looks like a regular, boring, old RC circuit like we had a minute ago. And it'll charge up just like we were talking. But what's going to happen is when I switch the switch to position B, well, now this battery over here is part of an open circuit. It doesn't even matter. And now I've got a resistor and a capacitor, but no battery. So what I want to think about is how that's going to work. So let's start off and put the switch in position A, and let's leave it there for a long time. Now, what's going to happen is if I put that switch in position A for a long time, current's going to flow out of the battery. onto the capacitor. It's going to charge that capacitor up. And if you wait a long enough time, there's going to be so much charge on this capacitor that the voltage across the capacitor will be the same as the voltage of the battery. And at that point, the current will equal zero, right? We've got basically no more current flowing. And the capacitor is fully charged. It's equal to Q max. Now, we flip the switch. We disconnect A and connect it to B. So now all this is broken. That current goes away. But now what's going to happen is all the positive charges that I have built up on my capacitor and all the negative charges that I have on the opposite plate, they're attracted to each other. These positive charges want nothing more than to cancel out those negative charges. Now, they can't hop the gap and cross the capacitor plates, but by connecting here to point B, now there's a path for these positive charges to travel through the circuit and cancel these guys out. And so that's what they're going to do. So you're going to end up getting current. It's going to flow this direction as charges flow through the resistor around through here and cancel out those negative charges. And that means if you do the loop rule, you're going to have something very similar, right? You're going to have your capacitor acting kind of like a battery. If I go from here to here, that's a voltage increase of Q over C. I'm going to have a voltage drop of IR. So it's like the same sort of loopy equation that we had before, and the same kind of reasoning is going to work. Because when I first hook it up, Q is going to be really, really big. The capacitor is fully charged. But at that moment, there's not going to be any current. But then as time goes on, Q is going to get smaller and smaller and smaller. I is going to have to get bigger and bigger and bigger and bigger. And so what's going to end up happening is this guy is going to also change with time in a similar fashion to how it did when it was charging up. It's going to discharge in a very similar fashion. And again, I'm going to have to do some calculus to prove this to you. So just take my word for it. But while it's discharging, the charge on the capacitor is going to look like that. Notice when time equals 0, e to the 0 power is 1, I have Q equals Q max. So graphically, it's basically just the reverse of what it was like it was charging up. When it was charging up, it was like the same curve kind of flipped upside down. It's reflected. So this is what it's going to look like when it's discharging. The current looks exactly like it did oops, still wet. There we go. The current's going to look the same sort of way. It's the same current equation we had a minute ago, if you ignore the smudges. So that's the idea. Take a second. I need to take care of a thing real quick. I'm going to pause for a second. Darn it. Except I can't control the stupid thing. All right, so we've got the behavior of this thing down as it charges up, as it charges down. Let's put this to practice. Let's figure out some stuff. So imagine, damn. Imagine that I've got an RC circuit and I tell you that I've got a, let's say, a 5 kilo ohm resistor, and a 200 microfarad capacitor are connected in series to an unknown battery. How long will I have to wait until the capacitor is, let's say, 90% charged? So I've got a series RC circuit. It's going to look like that. The problem, of course, is that I don't know how big that battery is. I know that this is 5 kilo ohms or 5,000 ohms, and this is 200 micro coulomb or microfarads. Hello. That's 200 microfarads, or 2 times 10 to the negative fourth farads. You want to convert it, right? And I want to know how long it's going to take till I'm 90% charged. But the problem is, I don't know what the battery is. I don't know what 100% charged is. I don't know how much charge I'm going to end up with. So how do I know what I'm taking 90% of? Well, it turns out it's not going to end up mattering, because even though Q max would equal uh, uh, C times V total, and I don't know V total, therefore I can't know Q max, it doesn't make a difference. If I'm looking for 90% charging, then what I'm really saying is that at some moment in time, Q, the charge that's actually on the capacitor, is going to have to equal 90% or 0.9 of whatever Q max is. So this statement is going to have to be true. And if I'm charging my capacitor up, I've got this expression. And so what's going to happen is I have two relationships now. I know this is true. I know this is true. So if Q equals this, I can take this expression and replace Q there. And you can see what's going to happen. Is that even though I don't know what the maximum charge is, since I don't know the battery, it won't matter because I have the same thing on both sides. If Q max was 1,000,000, then over here I'd have 90% of 1,000,000. If Q max was 1, over here I'd have 90% of 1. So as this side got bigger, this side would be getting bigger by the same amount. The value of Q max will end up canceling. And so all I've got to do is solve this expression for time. So look what's going to happen. I have I've got 0.9 equals, I don't need the parentheses on the other side anymore, so 1 minus e to the negative t over tau. So to get t by itself, first, let's get rid of this 1. We'll subtract 1 from both sides. So 0.9 minus 1 is negative 0.1. Now, of course, negative 0.1 equals negative whatever. If I multiply both sides by negative, I can cancel out those minus signs and make them plus. But I still have the problem of the thing that I'm solving for is stuck up in the exponent of that natural exponential function. And this is a place where I see a lot of students struggle because they've forgotten how to deal with exponentials. And in order to do that, I'll point out logarithms and how logarithms work. I've often found that students are like, I have no idea what a logarithm is. Logarithms are easy, and the concept of a logarithm is easy. So imagine that I have a log. Every log has a base. On your calculator, the default one is base 10. So the log base 10 of, let's say, 1,000 equals something. Now, you can put that in your calculator. It's going to tell you the answer, but you don't need a calculator for this one. It's so easy if you know what a log means, right? When I see a log base 10 of something, what this is really saying is the base to what power will give you this number. So 10 to what power equals 1,000? Well, there it's kind of obvious. 10 times 10 times 10, 3. So the answer is 3. Log base 10 of 1,000 is 3. Now you could do logs of other bases, right? If I do the log base 2 of 16 equals something. Again, what does this even mean? Well, let's say log base 2 of 16, I'm saying 2 to what power is equal to 16. And in that case, it's 2 times 2 times 2 times 2, 4. So the log base 2 of 16 is 4. Now, the natural log is basically just the same as writing the log where the base of the log is e, the natural exponential function. So what happens if I have an expression where I take the natural log of e to the, something, if I take the natural log of e to the something power, then remember what that means. This is the log base e, so I'm saying e to what power equals e to the power of x. Well, by God, what could this possibly be? Oh, I bet it's x, right? That's the idea. So when you take the natural log of e to the something, your answer is whatever the something is. It just gets the exponent out. So if I want to get this t out of the exponent and I've got e to the something, I can take the natural log of both sides. So on the left-hand side, I'm going to have the natural log of 0.1. And over here, I'm going to have the natural log of e to the something. It's going to give me just the something. And of course, the natural log of 0.1, my calculator can tell me that answer. I don't know what it is. But I can always solve for t by multiplying by negative tau on both sides. So negative tau times the natural log of 0.1 is equal to t. And there's my answer. And you might be alarmed for a second because you're like, wait a minute. I have t equals negative something, but time can't be negative. So am I in trouble here? And the answer is no, because it turns out that the natural log of any number that's less than 1 is going to be a negative number. So when I take the natural log of 0.1, I get negative 2.3. So if I multiply that by tau, well, wait a second. What the heck was tau? Tau was r times c, right? And r we said was 5,000. C we said was 2 times 10 to the minus 4. And of course, the natural log of 0.1 is that number I've already forgotten, 2.3. negative 2.3. So times 5,000 times 2 times 10 to the minus 4. Oh, actually works out to be exactly 2.3 seconds. So in less than 3 seconds, we're already 90% of the way to full charge. Because for this particular capacitor, the time constant was 1 second. Super easy. Any questions about that?
No.
No, we don't ask questions. All right. So that's it for capacitor circuits. That's the basic idea. So in terms of RC circuits, they're pretty straightforward. That's pretty much it for chapter 21. So the next exam is going to happen after we finish chapter 22. We'll probably take most of next week doing chapter 22. So you should expect the second exam to be not next week, but week after. As for the first exam, I said this at the beginning of the class, but some of you guys hadn't logged in yet. So just to make sure that you guys all get the message. I'm having some technical issues getting it posted. I'm not as aware of how some stuff works. There's a way I'm supposed to get you guys to be able to install Lockdown Browser, but I'm not sure how to set that assignment up. So I'm seeking guidance on that. So I may not get the exam up today like I wanted to, and if I don't, I'll just delay when it's due by some amount of time. So it may be due at the end of the weekend or even Monday or something. So I apologize for that, but I thought I knew what I was doing. I did not. That's probably going to be my epitaph, frankly. So that's where we stand. Are there any questions about the stuff that's going to be on the exams or the chapter 18 and 19 homeworks, or for that matter, the 20 or 21 homeworks, before I move on?
No, I'm fine.
Okay. If that's the case, I'm going to go end class a little early and go throw up. I will talk to you guys later.
Okay, hope you get better.
Yeah, thank you.
Have a good day.
Yeah, thank you. Bye.